Hello and welcome to this tutorial on the dynamic field architecture for reaching, and I will demonstrate how to run the simulation on your own computer with our simulation software Zibner, and hopefully this will help you to set it up or to understand the architecture better. What do we need for this? We actually just need the portable version of Zibner, which you can download as a zip file, and the architecture file in the JSON format. And it's probably also a good idea to read the paper where the architecture is published, which was submitted to the ICDL conference in 2015. Okay, but let's get going here. So if you download the Zibner application and extracted it, you get a folder called Zibner, and in that folder you'll find a link to the executable which you can run. This will open the Zibner simulation software, which has for now an empty canvas. So to open our movement architecture here, just go to File, Open File, and then sort of select the folder where you downloaded that. For me, this is in demo video here, and then just double click on that file. It might take some time to load the file, but after a while you should see sort of this canvas. And all these elements here, they reflect on the one hand dynamic neural fields or dynamic neural nodes with this circle symbol here, or most of these tiny boxes here are just transformations of the output of a field before it gets input into another field. So these things here are sort of static gains, so they weight the output, and this here is, for example, a convolution with a fixed Gaussian kernel. So you can examine each element in the architecture here by left-clicking it, and then on the right, which is called the property panel, you'll see all the parameters of that neural field here, for example, like the resting level, then the kernels that work here for the lateral interaction, but also the dimensionality of the field and the sizes. We have to discretize the field sizes, of course. And you can also always plot the contents of such a field by right-clicking on it, and then, for example, pressing the field plot button, which will then plot this here, which is a 2D field, so it's this kind of square, 50 times 50. But so to make it a bit more simpler for you, you can also open the plot group that is connected to the architecture, and you can find that button in the top here. And by clicking on that, all relevant plots for this architecture will be loaded. And depending on your screen size, this might look a little bit different, but you can sort of drag these around by left-clicking on them or changing the size by clicking on the bottom right corner here. So what are these things that I just pulled up here? You can start the simulation by pressing play, and for now nothing should happen except that the fields are now simulated, but no movement is going to be initiated yet. So you should see so how I will go through the different fields here. So the initial end effector position basically is a 2D field spanned across the movement plane, which is sort of the table plane you can see in the bottom here, our robot. And the reaching target has a peak of activation at the position of the target, which is in the simulation here, this green sphere. And then we also have, for example, the target end effector match field, where both this end effector position and the target position go in, but they are not strong enough on their own to form a subthreshold, suprathreshold peak. So they will only form a peak if they overlap, which will then determine the condition of satisfaction for our movement. Everything is not moving right now because the intention to move is also not yet activated, so it's at 0 here. I don't know if you can see that. And then another thing here is the oscillator, or the excitatory part of that oscillator, which is in relative coordinate frame, which is centered on the hand. So here you can see a peak in the top right, or not a peak, a subthreshold peak, a subthreshold blob of activation rather. And the top right means that the target right now is in the top right position of the hand. And once we will start the intention to move, a peak will rise here, and with the weight matrix connected to this oscillator, we will read out two velocities, one for x direction and one for y direction. So while doing the movement, you can see those here. But without further ado, let's just start the movement first and get this arm moving here. So for that, you want to start the intention, and we do that externally, and we use sort of these boost steps here, and you can find them if you click on tools and then boost control. Then you should get sort of a window like this, and then after you can initiate the boost by clicking here. So I will just do this for once. So you will see the intention going up here, and then the arm will move, and sort of a second arm will follow that. And I should explain that the first arm that moves is sort of the planned movement, so the virtual trajectory, while the real arm, the one that is connected to the muscle model, then just follows. And here it's really, the muscle model is really not stiff, so it will follow very slowly, but that's just for demonstration purposes. And you can also see, if I pause here, that the velocity profile of x and y sort of made this shift here with a peak velocity in the middle, and then went down to zero velocity, of course. And this will then also, but this is the virtual velocity that is not yet affected by the muscle model. If you then just want to restart the movement, you can just click on reset, which will move the arm back in the starting position, and also uncheck the boost here. So to run it a second time, just again click on the boost. The arm will move. You can see that in the current end effector position here. And also once the virtual trajectory overlaps, you can see here that a peak forms in the target end effector match field. So this is sort of the basic demo that you can do here, doing a simple movement. But you can also, for example, change the position of the target here. And for that, you have to access the two-step input. You can do that by searching for that two-step input in our architecture here, which is here. Or if you do not want to do that, you could, for example, also click on this little arrow here, which will highlight this. So if I would have selected something else, then click on the arrow, that should lead me to the two-step input. It's called two-step input, but in this example, we'll just have one input here. And these inputs are here set in a range between 0 and 50, which are the field coordinates, or in our simulation are something around 80 centimeters. And now you can change this here. For example, move the goal to 30-30, and now notice how the representation changed here, and also how the representation changed in the relative coordinate system, where the target is sort of to the right. And now you can just start the movement by clicking again on the reach button, and the arm should then move to the new target. And it's also a perspective thing here, so you can wiggle around here by left clicking inside and then dragging the table around. And that's it for now. So if you want to experiment more with this architecture, just download it. You can change certain parameters of fields. You can also use a two-step paradigm by changing the interstimulus interval to something greater than 0 here. I recommend something like 1200, which will then change, for example, we'll make this a two-step paradigm. So the first target will be at 10-10, and then after the stimulus interval is done, you will get the second target at the 30-30 position. Yep. that's it for now. So if you have any questions, just email me. I will write that email also down in the video description, and have fun with the architecture.